Hello everyone, welcome to Synthcrap. In the last episode we made a function block module which consists of a voltage controllable oscillator limiter, comparator and a dual function generator, which is a fairly useful module. But now we need something to mix those CVs generated by this module as well as the audio generated by the oscillator core. And for these needs, today we're gonna build the dual matrix mixer, a module that consists of two 3 input and 2 output matrix mixers. What is a matrix mixer? We'll find out later, but before we jump into theory, I have a little bit of an announcement. This episode of Synthcrap is the last monthly episode of Synthcrap. Sadly, I didn't receive as much support on Patreon as I wished to receive, and I'm a bit low on funds recently, and it seems that I'll continue to be. So as simple as that, I have no money nor will to make Synthcrap every month. I will continue doing this show, or at least synthesizer videos, but not in this format. I think they're gonna be smaller, but on the bright side, I will release the materials publicly, not only for my Patreons, because the Patreon's closing down in a month. Thanks to everyone who supported me for this time. Now let's find out what matrix mixer is and how it works. Today we're gonna build a matrix mixer, which is a very helpful and useful thing for modular synthesizer, and it really enhances its capabilities both in processing CVs and audio signals. It's basically a mixer, say 3 inputs, 3 volume knobs, and output. This is a simple mixer. If we add another row and the same signals go into these 3 knobs and go to the other output, it becomes a matrix mixer. These, see, you have an LFO here, envelope generator here, and envelope generator here. And here you have VCF, which stands for voltage controllable filter, and here you have VCA, which is voltage controllable amplifier, and you can find these on most analog synthesizers like Korg MS-20 and so on and so forth. What you can do with this matrix thing is you can put a little bit of LFO on the VCA, one envelope on the VCA completely, and the second one like half, and then you can put an LFO on the filter, turn off the envelope generator 1 for the filter completely, and then turn on the envelope generator 2. First thing we're gonna need today is an inverting amplifier. In the previous episode, we looked at the non-inverting amplifier configuration of the op-amp. Now we have an inverting configuration. It's easier than the non-inverting. It's the voltage input resistor minus, and this is the plus, which goes to ground. This is R, this is our feedback. The voltage amplification coefficient of this inverting amplifier is R feedback divided by R with minus. It's an inverting amplifier, keep that in mind. So if you put minus 2 volts here, this resistor is 10 kilo ohms and this is 20 kilo ohms, you will get 4 volts at the output. If you have 4 volts here, you'll get minus 8 volts output. Get it? This little amplifier circuit will help us recover the signal from the passive mixer network. It's a passive mixer. You basically put 3 signals in there, or 4 or 5 or however many you want, and you get the output, but each of these signals gets divided by the number of the channels. So say if we have 3 volts here, 9 volts here, and 12 volts here, here we have 1 volt plus 3 volts plus 4 volts, because each of these get divided by the number of the channels, which is 3 in our case. Or basically, this is the same as 3 plus 9 plus 12 divided by 3. This gives us this. A little amplifier at the end of this circuit allows us to mix signals without actually dividing them in any way. So at the output of this kind of mixer, we would get actually 3 plus 9 plus 12 volts with minus, because this is an inverting amplifier. So if the input signal stayed the same, we would get 3 plus 9 plus 12 with minus, because this is an inverting amplifier. But this amplifier has its power supply rails, right? So, like, we power our amplifiers at the Euro rack with plus minus 12 volts, and in our system we power it from plus minus 8 volts. So, say here we have 8 volts, and here we have minus 8 volts, and this is, it's 24. Minus 24 is like really lower than minus 8, and thus the amplifier will clip the output to minus 8 volts. So unless these three inputs result in a number that's more than minus 8 volts or less than 8 volts, it will be clipped to these values because of the power supply. How can we evade that? Well, the answer is simple. We just need a volume control at the input of each channel, so we can trim the volume and then get a non-clipping value. Now we will have two channels, one here and one here. But for each of them we will have our signal going through a potentiometer. Oh my god, what am I drawing? It's like this here. We choose how much of the signal goes into the ground and how much of the signal goes into the actual circuit when we turn the knob. This is our potentiometer. Google it up if you don't know what's a potentiometer. We get our values trimmed by these potentiometers and then simply summed, as we had it summed before, by the operational amplifier, and get a clean, cool, buffered mix. If we clone this circuit right in front of itself and put these inputs right into the next circuit, we will get a 2x2 matrix mixer. The same thing would happen to the 303 matrix mixer if we add a third channel. All clear? Good. Now to the polarizer function. So first of all, let's talk about what the hell is a polarizer. When you have your knob called volume, it goes from 0 to 10. Okay? But when you have your polarity knob, it goes from minus 10 to 10. What we have here at volume is, at this position it gives out nothing. At this position it gives out our full signal. If we have a sine wave at the input, like you can have a square wave and then it would be a square wave, obviously. Okay, if we set it like at 5, it would be about half of that volume. But if we put our sine wave, the same one, into the polarizer, when it's at minus 10, it would give us the opposite to what we have here. So if we dial our knob to 0, which is in between minus 10 and 10, our polarizer would obviously give out nothing. Then when we crank it up to 10, it would give us the sine wave we had in the original input. Why would you need this? Well, imagine you have two oscillators and one LFO, and you want to make a cool drone, very static analog. So you take the LFO and put that into both oscillators. But that sounds kind of like, you know, annoying and not really interesting, and who needs that? But if you have a polarizer, you can polarize your LFO so it goes like this for one oscillator and like that for the other oscillator, and then you can plug one oscillator into the pitch control of the other oscillator. And then, okay, stop. Well, we got the main idea. Now, the easiest way to make a polarizer would be to take an input signal and then divide it into two paths. One is a simple buffer, and the other is an inverting buffer. Then send them to a potentiometer, and the potentiometer will choose which one of these two buffers we listen to more, to the inverted or to the non-inverted. But we're gonna do it a little bit differently because we want this thing to be both the polarizer and the attenuator, which is the simple volume control. So our volume control is going like this. Signal output, ground. Here is input. We turn the knob towards here. We mute the signal, we turn the knob towards here, we hear the full signal. Okay? Good. Now, if we want to make this a polarizer, we want to put this through an inverting buffer, then put this through another inverting buffer, and into this midpoint we pass our signal from here. So what happens there? We choose how much of the signal passes original and how much of the signal passes inverted, and then it inverts once again for buffering needs. So what we want to do here is to put a switch which switches between ground and our inverter network. So if this switch is in this position, this potentiometer's side is grounded, and it acts like a simple volume control which inverts the signal, then inverts it once again, and we get our clean signal. If we put the switch in this position, we get a polarizer which allows us to invert the signal at our will. Now these inverting buffers are exactly what you think they are. They're just inverting amplifiers with voltage gain of 1, which means here is plus, here is minus, plus is grounded, minus inverting input is fed with the signal. If these two are equal, the voltage gain is R divided by R with minus, which gives us minus 1. Then we put another inverting amplifier right here, and this is going to be our output. Here is R and R as well, so we invert it back. Right into this point we put our second end of our switch, which allows us to use this both as an attenuator and as a polarizer. So there is one more important thing we can do to this circuit. We can actually make this a mixer and a polarizer at the same time, and this is done in a very simple way. We just need to... But first, let's call this piece of circuit the inverting operational amplifier with a gain of -1 and inverting buffer. So whenever I put this into the circuit as a box with an input and output, you know that it's just an op-amp set in this inverting amplifier configuration with the gain of -1. So now we have our input 1, input 2 and input 3. We add a resistor equal to those in these buffers, and then put them on all two potentiometers, and we literally just join the top parts of these potentiometers together and put them into the first inverting buffer. Then we take the lower parts, the lower pins of these potentiometers, and join them together as well, and pass them into a switch with one pin grounded and the other pin going up there. So you see, it's basically the same as just a polarizer or attenuator with a switch, but it has 3 channels, which is already a mixer. Next step is just copy this thing a few times and get a matrix mixer. Literally just put these same inputs into every other mixer, and we get as many rows in the matrix mixer as we want. I'll go with 3x2 with 3 inputs and 2 outputs.
Here's the final schematic. It's literally what I've just drawn, but in details. This circuit was engineered by Doepfer, the company that established Eurorack format. It's very simple, it works, and I decided to go with this circuit, even though there are much more complicated matrix mixers with VCAs and so on and so forth. This one is very simple and reliable, so we'll go with that. And then the assembling routine began. As always, making the panel, making the board, soldering up the board, but this time without the wiring. Simply because there is no wiring to be done. This time I decided to mount the PCB not on the potentiometers, but on the banana jacks. And there is no need to solder up the banana jacks because they're simply tied to the PCB. Truthfully speaking, I don't want to cover all the aspects of etching the board and soldering up the board and so on and so forth again, simply because I did it in the previous episode, so you can go and watch it if you really want to know how it is done. And today I'd like to spend more time showing how to work with this thing, so let's better look at this thing at work. Okay, so here we have our matrix mixer, and we already have the FN blocks function generators patched into LFO mode, so we can use that directly. We take the output of function 1, put it into the first channel of the mixer. Then we take the output of the second function, put it as the second input, and then we take the output of a slow oscillator and put it in as a third input. Then we take oscillator red one and we listen to it. And thanks to Matrix Mixer, we now have a chance to make so many different stuff, from glitchy textures to drone to sequences to many more, up to you to explore. Thank you for watching me, and see you soon. Bye bye!